Today we are discussing probability, and you might have remembered from my volume video that I mentioned that was one of my favorite applications of the integral. Well, here is the other. Now, I will say that probability is a huge topic, and you could not only spend a whole semester on it, you could spend a whole career on it, and we are just touching on it for this course. So we will introduce some basic terminology and do some examples, and then you can work on a worksheet to get the idea of it. And I hope that you enjoy it and you take further probability in the future, or you use it in the future, this kind of thing. So first of all, what we are focused on, because this is Calculus 2, is continuous random variables. And let's see a few examples of these. So this would all say, you could put random in front of the noun. So age of a random person in years, the height of a random maple tree in feet, the waiting time at a doctor's office, the lifetime of a light bulb. So this is in minutes and hours. These are all examples of continuous random variables. Okay, so what is this? These are typically denoted X, capital X. And you can think of a continuous random variable as just a mapping. So this is a mapping of a random process to an outcome. So the random process, for example, if it's the age of a person in years, is capital X, it would be maybe pick a random Boston resident and figure out their age, either by asking them or checking their license, something like this. Or walk into a cafeteria, pick a person at random and find out their age, like this, okay? Or for the lifetime of a light bulb in hours, you pick a random light bulb coming out of a factory, and then you plug it in, and then you just measure, right? This is the mapping of a random process to an outcome. Now, we are focused on continuous random variables, which means the continuous part of the random variable, it means the values range over an interval of real numbers. These are the ones that come up in this course because we integrate to calculate probabilities, as I will get to momentarily. Okay, so this is what the continuous part means, and you might think that, well, the age of a person in years is not in an interval of real numbers. It's only, say, 0, 1, 2, 3, etc. But really, it is in an interval of real numbers. I am 40, but not for long, because in a couple of weeks I turn 41. But even if today was my birthday and I was 40 today, I wouldn't be 40 exactly, because I wasn't born at exactly this moment, right? So your age is really over an interval of real numbers. I would be 40 point and then a big decimal, for example. Okay, now there's one more piece of notation that I would like to discuss, and let's just ask a question, and this will lead us to the notation. So let's suppose you walk into a doctor's office, okay, you can say on some random day that you happen to have an appointment, okay? And the question is, what is the likelihood okay? And now I'm going to bring in the math term, which is probability. Suppose, I didn't say it was me. Let's suppose I walk into a doctor's office. Okay, what's the likelihood or probability that I wait 15 or fewer minutes? I wait 15 or fewer minutes. Now, what's the notation for something like this? Well, the notation, okay, maybe before I discuss notation, let's mention this word now, because this is the whole topic of this lesson. This probability, well, probability is a number between 0 and 1. So this is always between 0 and 1. If you have probability 0, it says there's no chance that if it happened. If you have probability 1, it says 100% that will happen, okay? And the notation here, if capital X is this random variable, the notation is the probability that 0 is less than or equal to X is less than or equal to 15. Okay, so this is the notation for this question. And I mean, I'm not going to have an answer for you because I haven't discussed probability density functions or anything like this, but that's coming next. Okay, so this is the notation. The probability that this random variable of this one, the wait time at the doctor's office in minutes, is between 0 and 15, like this. Okay, so now we have a little bit of understanding of what we're calculating. We're only working with continuous random variables, capital X. So let me now define what a probability density function is. And then we will do some examples. Okay. Well, before I define it, let me just make a comment. And it's as follows, that every, let's say, continuous random variable, capital X, has what's called a probability density function. F such that if we want the probability that X is between A and B, okay? So this random variable is between these two numbers, A and B. Maybe it's X is the age of a random person, and you want to find the ones that are between 10 and 30, for example, right? Or find the probability, I should say, that the random variable lies between 10 and 30. Okay, such that, okay, this is the integral a to b of f of x dx. And this is, we integrate to calculate probabilities. Okay, that's what this is saying, that if you want to calculate a probability for a continuous random variable, that you integrate its probability density function. Okay, well, let me define this for you. So we can start the other way, and we can just take any function. As long as it satisfies a few properties, then it will be a probability density function, meaning that when you calculate integrals of it, definite integrals or improper integrals, you're calculating probabilities for some capital X. So this is the definition. So a probability density function f of x is, well, let me say it this way. Okay, maybe continuous, but we'll just say a function. We just need to be able to integrate it on minus infinity to infinity, or on the real line, such that we have two conditions. The first one is that the function must be greater than or equal to 0 for all x. So it must be non-negative. And the second condition is if we integrate minus infinity to infinity f of x dx, we get 1. Now, what are these going to give us, these two together? First of all, my function is non-negative. So I really want you to think, when you're looking at something like this, it's really area, right? This is area under the curve because we have a non-negative function. So that probabilities are giving us areas, or areas are giving us probabilities, whichever way you want to say it. And moreover, we see that this will always be greater than or equal to 0 because my function is never negative, but then the total area under the whole curve minus infinity to infinity is 1, which says that all of these probabilities that you calculate will be less than or equal to 1. Okay, so this is what it means to be a probability density function. Now let's do some examples. I'll do one example and then I will calculate, or mention I should say, a few measures of central tendency, and then we will do a few other things. Okay, so here is an example. Let's take f of x to be, let's say 3x squared for 0 less than or equal to, or I can just say less than x less than 1 or equal to, and then let's say it's 0 elsewhere. Okay, so I will graph my probability density function. It's certainly defined on the whole real line, although it's only non-zero on 0 to 1. So if I graph this, here's 1, it goes up to 3, and it's x squared. So it's going to be something like this, okay? And then it's 0 everywhere else. Maybe I should have done it a different color. So then it's 0 out here, it's 0 back here, and then this is my curve here. I'm trying to outline it in green here, like this, okay? This is certainly satisfies that the function is greater than or equal to 0 on the whole real line. And then, so we can check, I'll check in red, these two conditions to show you that this is a probability density function. Okay, well, certainly f of x, this is what I just mentioned, is greater than or equal to 0. That's the first one. The second one, if we integrate minus infinity to infinity of f of x dx, well, this looks like it's going to be improper, but it's really not, because everywhere the function is 0, well, you integrate 0, you get 0, right? So the area only lives between 0 and 1, right? So this is an integral 0 to 1 of 3x squared dx, okay? Because, as I mentioned, everywhere else the function is 0. So if you just took the total area minus infinity to infinity, well, it would just be the area over this piece. And this is x cubed evaluated between 0 and 1, which is 1, okay? So this, in fact, is, we see the definition, I'm about to erase it, but it is, in fact, a probability density function. Okay, wonderful. Well, let's calculate a probability, perhaps. So let's find, for this probability density function, let's find the probability that 1/2 is less than x, I'll do it this way, less than or equal to 1. Okay? Now, let me graph it first, and then we'll calculate it. So 1/2 is maybe right here. Every time you think probabilities, you think areas. At least I do. In fact, Whenever I teach like Calc 1 and we start talking about area under the curve, my mind is always probability because that's always what I think of. But in any case, this probability is this area here. It's the area under the curve between 1/2 and 1. Okay? Well, this is an integral from 1/2 to 1 of 3x squared dx, which we already have an antiderivative. We get 1 minus 1/2 cubed is what? 1/8. We have 7/8. Okay, so that's the area here, or equivalently this probability. Okay, let's see what comes next. Okay, well, let me make a comment because this is quite important. Let's say we take even this exact same function, or maybe I'll even work more generally. So the way that I defined this, I said the probability that a is less than or equal to x is less than or equal to b was this, the integral a to b of f of x dx, where little f is the probability density function. But what about, let me do a few things. What about this? And then what about this? And then what about, okay, I think I have all possibilities. You see the difference here? I'm just slightly changing. So in the doctor's office example, this would say I wait, more than 0 and less than 15 minutes, right? Or here I wait strictly less than 15 minutes, or less, at most 15, but more than 0, right? So it's whether or not we're including the endpoints or not. Well, if we think about area, what happens if I just remove this one right here? And I change that, and instead of having it be a solid line, maybe I'll do it in black, it's now dotted. What happens to this area? What's in my picture now would be this one. The area doesn't change, right? Or if I put dotted here instead of solid, area doesn't change. All of these are all equal to this definite integral. So all of these are all equal to the integral a to b of f of x dx. You remove this one line out of an area, the area is not changing. Another way to think about that is what all of this is saying. If all of these are the exact same value, it's saying, for instance, the probability that x is just a. Well, this is this. It would be just adding this line or not, right? Well, I'm claiming that this is 0. And why is that? So this is my claim. Well, the reason, if you want to think integrals, okay, fine. The reason this would be an integral from a to a of some function dx, and you see the upper and lower limits are the same, which is 0. Okay, that's thinking it in terms of integrating. You can also think about it in terms of area. You have this single value down here, a, and okay, you can connect a line up to the function, but then you're asking for a two-dimensional area of this. Well, if you think, for instance, like length times width, the width would be 0. The two-dimensional area is 0, right? And this is something that is specific to continuous random variables. If you do go take probability, and you should, the discrete random variables are very different. They do not have this property. But with continuous random variables, the probability that you are any given value is 0. So if I walk into the doctor's office, what's the probability I wait exactly 10 minutes? It's 0, okay? Because probabilities are really two-dimensional areas. And the quicker you get that through your mind, the more, oh, something like this will make sense. Okay, now, what I would like to discuss, maybe I will come back to this example, in fact I will, I'd like to discuss some measures of central tendency for continuous random variables, and this will really take you back into what we were just discussing, which was center of mass, okay? So let's suppose X is a continuous random variable. We have two measures of central tendency, and I will talk about one, and maybe then I will see it in that example that we just finished, and then I'll talk about the other. Two measures of central tendency. The first one is called the mean, and this is denoted mu. Now, how do we calculate this? This is the integral minus infinity to infinity of x, f of x, dx. Now, let's go back to center of mass. And to do this, let's suppose we have a wire, a thin wire, that lies on the whole real line with density. Well, with density, this density function, probability density function. Okay, fine. This might be the density of a wire. In fact, it is. Then you have a wire. First of all, what's the total mass? Capital M, total mass. Well, you just integrate the density function, right? And we know this is a probability density function, and so by definition, this is 1. And then if we want the center of mass for the wire, well, we integrate minus infinity to infinity of x, f of x, dx over m, this capital M. Try to make sure it doesn't look the same as mu. And this is just this. X, f of x, dx. So in fact, this measure of central tendency, which is the mean, and I'm sure you've heard of that. Well, like the average on the test was whatever. Okay, that's a little different because it's not for a continuous random variable. That comes from a sample, but it's the same idea. But this mean really is the center of mass. If you think about this probability density function being density like on a long wire, for example. Okay, so that was just a nice comment that took us back to the last section. And it really is where this comes from in probability. So this is a measure. It's where, for instance, if we had a wire with density f of x, where we would put our finger so that it balances, right? And this is one measure of central tendency. Now, let's go back to this example where we had f of x was 3x squared if 0 less than x less than or equal to 1 and 0 otherwise. And I'll even graph it again. The graph over here was like this, 1. This went up to 3, and it looks like a squared, like this. Okay, and then it's 0 everywhere else. So this was our function. So the mean here, mu, is the integral minus infinity to infinity of x, f of x, dx. But the nice thing here is my function, right? This is thinking about the graph of the density, and even if you thought about this as being a long wire, the density really only lives between here and here. So this integral is 0 everywhere except 0 to 1. So this is an integral 0 to 1 of x times 3x squared dx. And this gives me an integral of 3x cubed. We get 3/4 equals, so we have 3/4. So our mean, which is just one measure of central tendency. If we have a half here and 3/4 here, it would be, well, maybe it would be here. If we think about a wire, right, with this density, but this is mu, okay, 3/4. Okay, this is the mean. Now, the next measure of central tendency is also quite important. It's a median, little m. And this you are also very used to with exam scores. What's the median? Well, if you have a sample, well, it kind of depends if you have an even or odd. Let's say we have an odd number in a sample. It's the very center one. If you have an even number, there's different formulas. Sometimes you take the 2 in the middle and average them, or there's different ways you can calculate. But this is the concept of a median. Now, what would it be for a continuous random variable where we have a probability density function? Again, we really want to think area. The median, so this is such that m, I'll say, is defined such that if you integrate from minus infinity to m of the function dx, you get a half, or equivalently, you could write it this way, and sometimes it's easier to work with one or the other, m to infinity of the function dx, that this is 1/2. What is this saying? Right, we know the total area under the curve is 1, and this is saying the median, well, some x value such that half of the area is on one side, half of the area is on the other side. This is the median, right? This is saying that this one says half the area is to the left. This one says half the area is to the right. Well, I should say the area to the left is 1/2, the area to the right is 1/2, but the total area is 1, so these two are saying the same thing, but sometimes it's easier to work with one or the other. Okay, this is the median. Now, if I go back to this example here, maybe I can even fit it above. Well, how would we calculate the median? I'll put a line. So the median for this example, the median, we would integrate. So in our example, we integrate. I'm going to start, well, I'll do this one. Minus infinity to m f of x dx. This would be a half. And then I solve for m. Well, here, again, I have nothing down here, right? The function is 0. So I have no sort of density on this side, or there's no area under the curve. Similarly, up here, this is just the integral, 0 to m. I could have also gone m to 1. That would have been over here, but I chose to go 0 to m just because evaluating things at 0 is pretty, not too hard. Although, let me put the function now, 0 to m of 3x squared, okay? So this would be x cubed from 0 to m. We have m cubed, and this should be equal to 1/2. So we have m cubed is 1/2, and so m would be 1 over the cube root of 2. And now let me see if I have this worked out. That's not something that I have in my mind. Let's see. Oh, it's approximately 0.794. Okay, so the median here is bigger than the mean. The median is, I don't know, bigger. This is 0.75. The median is somewhere like this. This would be the place where half the area is on this side and half the area is on this side, okay? My picture is not very accurate, but you have the idea. It's just a little bit bigger than the mean. Okay. Well, now I'm going to talk about a name distribution, and we will work a little bit with that. And then that will be about the end of this discussion of probability. The one named distribution I want to discuss is that of the exponential random variable. And this is probably my favorite. This is my favorite type of random variable. So here, an exponential random variable, and this has the parameter being the mean, mu. Okay. So this has probability density function as follows. F of x is 1 over mu e to the minus x over mu, and this is for x bigger than or equal to 0, and at 0 otherwise. Okay, this is what an exponential random variable has this PDF. Now, let me get this example here. What I will say before I do the example is this random variable is known for modeling wait times. So this models wait times quite often. It can model many other things, but one that it comes up quite often is with wait times. So now let's look at my example. Instead of a doctor's office, we're going to be standing in line for an ATM. Okay. So example, the average wait time in line at an ATM is 2 minutes. And what's the probability a customer waits more than 3 minutes? And then we will actually show the mean is 2 by this. So what is the probability that a customer waits more than 3 minutes question mark? And then part B, we will have an exercise to see, in fact, that the mean is 2 here. And we will use the exponential random variable. So we can assume that this wait time is modeled by this. Okay, well, here, if the mean is 2, it would say, I will write it down, that f of x equals, it's a half e to the minus x over 2, and this is for x bigger than or equal to 0 or 0 otherwise. Okay, and so what I want to calculate here, I want the probability that x is bigger than 3. Okay, and there's a few ways we can do it. I will do it just directly looking at this. This would be an improper integral. So this would be an integral from 3 to infinity of 1/2 e to the minus x over 2 dx, okay, which is a limit as b goes to infinity, the integral 3 to b of 1/2 e to the minus x over 2 dx. Ooh, we're running out of space. Let me move. I'm probably blocking it also like this. Now, how do we calculate this integral? Well, we keep, maybe I will leave myself more space here, equals. It's a limit as b goes to infinity. And when you integrate minus x over 2, well, generally, where can I remind us? I'll put a box over here to remind us. If we integrate e to the ax dx, it's 1 over a e to the ax plus c, right? You can do the substitution if you want, but this is the integral of e to the ax. We have a here is negative 1/2. So when we take 1 over negative 1/2, it's the same thing as multiplying by minus 2. So here, we're going to have a negative e like this, because the minus 2 times 1/2 becomes just negative 1, and then evaluated between 3 and b. This is a limit as b goes to infinity of, we have minus e to the minus b over 2, and then we have plus e to the minus 3 over 2. Okay? Right, I was making sure I didn't have any mistakes here. Now we take a limit. Well, here, this is a e to the minus b over 2. The graph of this, maybe I'll come back over here to my side box. The graph of e to the minus x, say, fine, looks like this. Y is e to the minus x. So as x gets very large, or b gets large in this example, e to the minus b over 2 goes to 0. So this part goes to 0, and I am left with e to the minus 3 over 2. Now the question is, and let's see what this is exactly, this better be a number, I'll move, this better be a number between 0 and 1. And in fact, in my calculator I have this as 0.223. So this is the probability here, this, but it's approximately this. It's the probability that the customer will wait more than 3 minutes to use this ATM. We will show the mean is in fact 2 using the definition of the mean. Right, I just said if you have mean mu, this is the formula, but I didn't actually verify anything. So now let's do the same example. So we have f of x equals is 1/2 e to the minus x over 2. And this is for x bigger than or equal to 0 and 0 otherwise. So this is a probability density function for the exponential random variable with mean 2. I mean, I just said that, but let's actually verify the mean is 2, okay? And then I think that will be about it for this little mini lecture on probability, and you can work through some problems involving these concepts. Okay, this is our last honors topic of the semester. It's hard to believe we are nearing the end. Okay, well, the mean is, okay, it's an integral, minus infinity to infinity, x, f of x, dx. In fact, I was just thinking about, I never even verified that this was a probability density function. Certainly it's always non-negative because e to any power is always positive, although it can also be 0, so this is always non-negative. Maybe that's an exercise for you to verify that this particular one has total area under the curve 1, okay? Well, in any case, we want to verify the mean is 2. So this is an integral. Well, my function only lives on 0 to infinity. It's 0 everywhere else. So this would be just 0 to infinity of x. And then we have 1/2 e to the minus x over 2 dx. Now, if you stare at this should say liate, all right? This is integration by parts. Oh, gracious, I got too excited. Sometimes that happens. Okay. Especially when I'm integrating by parts. Okay. Time to focus. Well, we did not have a log inverse trig. We have, okay? So I'm trying to think how I should group. Maybe I'll just group it like this and like this. You could pull the 1/2 all out, or you could group it with the x, but I'll leave it literally grouped as it is here. So maybe first let me come to the side. How do I want to do this? Indefinite first? Yeah, we'll do that here maybe. I'll come to the side right here. And we will calculate this. X times 1/2 e to the minus x over 2 dx. The improper integral, indefinite integral. And then we will go here, which is a definite integral and a limit. Okay, so here, u is x, dv is everything else, so it's 1/2 e to the minus x over 2 dx. And then we differentiate, and then we integrate. This one we already integrated. It was a minus e to the minus x over 2, like this. But if you didn't remember, you could integrate it again. And then by parts says uv minus the integral of v du. Okay, so we have, this is equal to uv minus x e to the minus x over 2 minus the integral of minus e to the minus x over 2 dx. Right? uv minus the integral of v du. Okay? And now, this is minus x e to the minus x over 2. And then I'm going to keep the minus because when I integrate this, I'm going to be multiplying by -2, which will make this positive. So then I will have a 2 e to the minus x over 2 plus c. Okay, now let me make sure I didn't make a mistake. I will check my notes because the minus signs will get me every time. Okay, good. That's what I got in my notes too. Wonderful. It's very easy to make a mistake with a minus sign, and the negative thing about taping like this is I don't have one of you to tell me, hey, you did it wrong. So I sometimes have to check. Okay, so now mu is a limit. As b goes to infinity, the integral, well, we already have an antiderivative, but maybe I will write this step. X times 1/2 e to the minus x over 2 dx, which is a limit. I'll go to the next line so I have enough space. This is a limit as b goes to infinity of, well, I have an antiderivative. So this is minus x e to the minus x over 2 minus 2e to the minus x over 2. And I evaluate between 0 and b. Okay, this is a limit. I like this, like I said, a lot of probability, or at least can be. It's a very nice put back in your brain how we do improper integrals, which is definitely something coming back to us with our final only some number of weeks away. Okay, so then we have minus b e to the minus b over 2 minus 2e to the minus b over 2. And then I subtract, evaluating at 0. Well, you see this first term, when you evaluate at 0, there's an x in it. So this first term at 0 is 0. And this one is going to be a plus. We're going to have 2. I'll go ahead and write it, e to the 0. We know e to the 0 is 1. Okay, now we are almost there. In fact, we're in really great shape. This one here, we looked at something similar, right? As b gets very large, e to the minus b goes to 0. And similarly with e to the minus b over 2. So this term goes to 0. And now let's think about this term. It's not exactly L'Hopital because this is going to infinity, this is going to 0. But how could we see it? We could write here, I'll put my side work box back. If we want just the limit of this first term, we could write it this way. b goes to infinity. Put this in the numerator. Put e to the minus b over 2 down here. Uh-oh, this would be positive here. Right? These two are now the same. Now, well, numerator is going to minus infinity. I think I said infinity before. I meant minus infinity. Denominator is going to infinity. You could do L'Hopital, where you take the derivative of the top, take the derivative of the bottom. Maybe I will do that here because I have the time. This would be minus 1 over derivative of the bottom is a half e to the b over 2. This is a chain rule, right? It's not a power rule. Derivative of the inside function is 1/2. Now you see the denominator is growing without bound. The numerator is fixed. This limit is 0. Another way you could have done this, and this is something we discussed in our sequences section, is that the denominator is exponential. The numerator is polynomial. The denominator is growing significantly faster, and you could conclude that the limit is 0. But if you don't remember that, you can always do L'Hopital. So you see here, going back to this, we have calculated this goes to 0, and therefore the limit is 2 e to the 0, or 2. So we have shown here that the mean is 2, right? Okay,